So integrated pest management. Basically, I'm going to talk about three things. First, I will talk about prevention, because in integrated pest management, one of the pillars is actually prevention. So I will talk about how we can prevent pests from building up so that they don't destroy our crops. The second point or pillar is the monitoring. So I will talk about how we can monitor these pests. Which I think I will have to unpack later on after this integrated pest management. That monitoring may form a lecture on its own, or I will have to combine it with a prediction or forecasting yield losses due to pests. The third part I'm going to talk about is intervention. So when we talk about integrated pest management, there are three things. Number one, we are talking about prevention. Number two, we are talking about monitoring. And number three, we are talking about intervention. And remember, we are talking about all pests, insect pests, plant diseases, and weeds. So let me start to present management. What is integrated pest management? Integrated pest management is the use of multiple control measures which are compatible, economical, environmentally sound, and culturally feasible for managing pest populations at acceptable level. This is actually a definition by somebody known as Tweed in 1979. So why is IPM important? We have a global population which is on the rise, and therefore there is a food demand because of the population rise. This means that farmers have to increase crop yields in order to satisfy this demand. But as the farmers increase these yields, they should try to protect biodiversity. So there is a concern about the environment. Now, IPM provides farmers with the tools and the strategies to maximize production sustainably and also to minimize losses to insects, weeds, and diseases. So what are the integrated pest management components, or simply IPM components? So I said we are going to talk about prevention. That is the number one pillar. So we have to prevent the build-up of pests. Then we need to monitor the pest monitoring. It's another pillar. So pests have to be monitored. We need to understand their populations. We have to do some scouting, looking for insect pests, diseases, and the weeds, so that we can determine when we should actually control them. Then intervention. This is when we have to implement control measures. This may involve physical, biological, or chemical methods, so that we keep the pests at a population which is not going to damage or to decrease crop yields. So please remember that when we talk about integrated pest management, first we are talking about prevention. That is the first point. The second point is that we are talking about monitoring. And finally, we are talking about intervention, coming in with various control methods. So let us talk about prevention. What can we do to prevent the pests from building up, so that they cannot threaten our crops? First, we can focus on planting dates. For example, in cotton, planting dates are chosen in such a way that the major flowering and the ball development periods do not coincide with the period of when the bollworm, particularly the red bollworm, are at high incidences. So we can manipulate our planting dates so that the flowering and the ball development doesn't coincide with the high incidences of the insect pests such as red bollworms. Early planting after the recommended dead period sometimes will allow the cotton crop to escape the red bollworm damage. If we do early planting, of course, soon after the dead period. Plant pests and diseases in cotton, you've got some regulations which were promulgated in 1988. Now, these regulations enforce the creation of a dead period. You are growing cotton, and it has to be destroyed. That is the closed season or the dead period. Now, this is done in order to disrupt or prevent the pink bollworm so that it cannot build up a population which will threaten the cotton. So we have got legislation which can help us to prevent the red bollworm infestation in the cotton. Still, this is based on planting dates. Probably this can also apply to other crops. There's a trap cropping. We can also use trap cropping to prevent the buildup of pests. Now, trap cropping and the planting diversionary hosts have been widely applied and recommended in the past. But for cotton, the use of maize and sorghum has not been very effective. These two, in some cases. However, Mapranga in 2015 reported that sorghum, maize, and cowpeas were good trap crops for the African bollworm. They are generally most preferred hosts for oviposition and larval development. So where we grow cotton, if we grow these crops, this can help to divert the African bollworm from cotton. Trap cropping can also be applied to parasitic weeds. In this case, we can grow cowpeas, soybean, groundnut, and bambara nut as trap crops for striga species. So what happens is that when you grow these crops, they will produce some root exudates, which will cause the striga seeds to germinate, but the striga will fail to get attached to the roots of these crops, and the striga will eventually die. We can actually use crop varieties to reduce the incidence of pests. There are certain crop varieties with resistance or tolerance to pests, and we can actually grow these varieties. It is one of the most important factors in IPM. For example, we have got hairiness, which is a major factor for resistance against the sucking insect complex of cotton. So we have got cotton varieties which are resistant to lepidopteran pests, as reported by Mapranga. So, whereas some of these cotton varieties may be difficult to develop, but such varieties could be useful. In sorghum genotypes, we have got the SAR29 genotypes, which we have found to be resistant to Striga asiatica. And the SAR29 could be used as a source of resistance to develop other sorghum hybrids with resistance. There are maize lines from IITA, for example, ZD05, which are resistant to Striga asiatica and Striga hemonthica. This ZD05 has actually been used to develop some maize hybrids with the tolerance or resistance to Striga species. There are also maize genotypes which are resistant to grey leaf spot and the maize streak virus. Some of these varieties are now being grown in Zimbabwe. We have the tobacco genotype T66, which was reported to be tolerant to Striga gesneroids, followed by T61 and KRK26. This was reported by Koga in 2011. So we could grow crop varieties which can reduce the incidence of pests, be they insect pests, plant diseases, or weeds, especially parasitic weeds. So the attempt is to try and reduce the build-up of pests in the fields by prevention. Let us talk about the BT cotton, Bacillus thuringiensis, or just BT resistant cotton. Now, the BT cotton is resistant to a number of bollworm pests of cotton. Now, the BT cotton can be used in the same way as host plant resistant varieties derived from conventional breeding programs. The adoption of BT varieties is not knowledge intensive, so smallholder farmers can grow them with ease. Like conventional host plant resistant varieties, BT cotton is compatible with the most IPM tactics. Now, the toxins such as CRY1AC, CRY2AB, and the VIP3A produced by BT cotton varieties are only ingested by the phytophagous insects. The toxins such as CRY1AC, CRY2AB, and VIP3A are produced by BT cotton varieties Now, these toxins can reduce the insect pest populations. Now, in order to reduce again or to prevent build-up of pests, we can utilize crop rotations. Crop rotations could break the life cycles of the pests. This could reduce crop pest populations by simply practicing crop rotations. For example, crop rotation is effective on red and pink bollworms, which have narrow host ranges. African and spiny bollworms are polyphagous, so will not be affected by rotations. So there are some bollworms which are not affected by rotations, but the red and the pink bollworms could be reduced by crop rotations. Crop rotations can also break disease life cycles. And I'm sure these crop rotations can also affect weed life cycles. Intercropping, two crops are grown in the same field, for example, maize and cowpeas. This could promote natural enemies for insect pests, which means we can reduce the use of insecticides. Maize intercropped with cowpeas was able to reduce Striga asiatica infection as reported by Kasembe. Also, Khan et al. In 2002 reported that intercropping maize with Desmodium cynatum greatly reduced the Striga hemonthica. Intercropping could also disrupt disease epidemiology. So plant diseases can actually be reduced by intercropping. Deep ploughing. Ploughing exposes a bollworm pupa to be picked by birds and excessive sun heat. The importance of ploughing cotton stubble to reduce overwintering populations of African bollworm was reported by Fitt and Forrester. We now know that post-harvest cultivation can destroy a pupa of bollworms. And this is now receiving some attention in this country. Harvesting and storage. Now, carryover of weed seeds and disease-causing organisms can be reduced with good harvesting, seed cleaning, and seed storage methods. So we can reduce these problems at harvesting or storage. Now, let us think about this issue, preserving biodiversity. We can argue about it. Protecting natural habitats near farmland is the best way to conserve biodiversity, including many natural pest enemies. You know, where we are plowing our fields, the areas surrounding the maize fields or tobacco fields are important for natural habitats. It could be for natural pest enemies if we want to do biological control. Probably natural enemies can have somewhere to stay. Because as we are applying chemicals in the fields, there's also a possibility of killing these natural enemies. So probably at the edges of the fields, probably these natural enemies may find a habitat. So we should not destroy these natural habitats. So careful management of farmland edges, including trees and hedges, is important for wildlife habitats, providing cover and refuge for beneficial insects and animals. Now, in India, they have what they call field bands. These are not cropped strips in rice fields, which can provide refuge for predatory spiders that can help to control several insects. I don't know how much of these farmland natural habitats which we do not crop, which surround our fields, how much they are contributing in terms of pest control. Probably it's something which we need to look at. So I am now through with the prevention. So on prevention, I was just focusing on activities or cropping activities which are aiming at reducing the buildup of insect pests. And probably I haven't exhausted all of the issues because it's quite a wide topic. Now, the other aspect, I've said IPM relies on prevention. The second part is monitoring. So there's a need for observing crops so that we can determine what action to take in order to maximize crop production and quality. So we need to keep on checking our crops. We have got decision-making tools which can range from peg boards. Now, a peg simply a board with some holes. And on these holes, you can insert pegs. Now, these pegs may indicate the development of pests, or especially insect pests. It is a simple board, although it can produce a very detailed information, but it can be used by farmers as a simple tool to track or just to have an idea of how much of the insect pests are in their fields. It's a simple way of doing it. From peg boards, researchers could use computers for this. And you can also have trained local experts who can use remote sensing technologies so that we can really locate areas where we are having problems with pests. So we can get real-time information on what is happening in the field. And this could be very ideal if you want to control our pests. Of course, there is also scouting for pests in the cropping fields. Actually going into the cropping fields and observing the pests, even counting these pests. We need to assess certain populations of pests which can justify control, which we call thresholds for pest populations. So monitoring is very important because it can give us detailed information about the pests. Or this is simply inspecting our fields so that we check for the presence of pests. Later on, we will talk more about some of these decision-making tools in more detail, because it can be a lecture on its own. Now, under monitoring, I want to talk about early warning systems, EWS, for cotton bollworms. Now, for this exercise, we can use light and pheromone trap catches so that we can trap insects and use them to predict abundance and outbreaks of these pests. So we need to catch these insects in the fields using these pheromone traps or light. We know insects are attracted by light. So you, after collecting a sample of insects, you have to find out which of those insects are pests, which of those are probably beneficial insects. Now, trapping insect pests like is useful as a quantitative measure, indicating the start of an infestation or a migratory wavy front, probably indicating the need to begin scouting for immature stages in the crop. So depending on what you catch in the traps, if you catch these H. amigera or cotton bollworms, you can decide whether to scout for the eggs in the crop. This can also give you an indication on when to spray your crops. So early warning systems for cotton bollworms, depending on the light or pheromone traps. So on the monitoring, this is it. I will talk more about it in another lecture. For this stage, you just need to note that we need to scout in our fields so that we establish populations of our pests. And from these populations, we can decide whether to spray or not, to control or not to control the pests. So that is the importance of monitoring. It gives us the level of pest infestation. And it can also give us early warning systems. An early warning system can tell us when are we going to get serious infestation so that we can control the pest. So monitoring and devising warning systems are tied together. Now, suppose we now have our pests. We should come with intervention. We should devise some control methods. There's a need to reduce economically damaging pests to an acceptable level. And this can involve cultural, physical, biological, and chemical control measures, either used individually or should be used in combination. Other things which have to be considered are costs, benefits, timing, labor force, and the equipment which is going to be used. The effects on the environment and on the social status should also be evaluated. Now let us look at the intervention methods which focus on cultural and physical methods. These could be things like uprooting weeds and the removal of diseased crops from the fields. The possibility of integrating cultural techniques with the careful use of crop protection products should be explored. For example, instead of replacing manual weeding entirely with herbicides, there could be a need of combining the two, mechanical methods with herbicides or hand hoeing with herbicides. We can also think about using biological control as an intervention to control the pests. This can include introducing beneficial insects or predators, applying microorganisms such as viruses, fungi, and bacteria, and also using pheromones to attract, trap, kill, or interfere with the insects' mating habits. So pheromones can, attract insects. So when you have attracted them in a certain area, you can either kill them or you could be interfering with the mating habits. Bacteria, fungi, nematodes, or viruses have also been mass produced to control some pests. The most common and successful one is this Bacillus thuringiensis, BT, which is a naturally occurring bacterium, which has now been used to control pests, such as caterpillar pests in vegetables, vineyards, and orchards. Now, with the modern technology, crops like maize and cotton can now express the insect toxin produced by this natural control agent. And this can actually control pests. So you can make cotton and maize produce toxins to kill insect pests. Here I've got a table where I've got predators which can affect the cotton bollworms. We have got this green lacewing larva which can eat eggs and young larvae of Varieties of the bollworm. Spiders which can eat larvae of all bollworms. Probably this is very commonly used. Ladybird beetles and their larvae, which can also feed on eggs and young larvae of the cotton bollworm. Assassin bug, which feeds on the eggs. Pentatomid bugs, which feeds on eggs and larvae. This is now biological control. Now, on the use of pheromones, we can have selective trapping techniques to monitor the movement of pests or changes in their populations during the season. Or we can use the pheromones to attract or lure and kill the pests. So with pheromones. We can also use pheromones to disrupt mating. Once we disrupt mating, we can keep populations under control of the pests. We are now familiar with the chemical control, where we can use chemical crop protection products, which we call pesticides. They can be fungicides, insecticides, herbicides, which can deal with the insect and vertebrate pests, diseases, and weeds. Now, they can also be used as part of the integrated pest management, chemical control. Now, let us talk about the IPM strategies and tools. Now, IPM may also involve computer-aided sampling and decision-making, as well as improved farm equipment. Apart from the use of chemical, natural, biological, and biotech products. Now we have got some of the programs which are quite sophisticated, which have been developed for pest control. For example, we've got these VG cultures, Empress, which were developed by FAO. We have got the GPS, which is grass pest control, also developed by FAO. Now, these strategies can also be introduced to developing countries. There is crop pest modeling. On this one, we'll talk a bit in the other last lectures when we talk about crop yield losses due to pests. So crop pest modeling models are conceptual or mathematical devices which aim to simulate natural processes so that we have an idea of how the pest is damaging the crops. So it's a model which is used to make us understand what the pest is doing so that we can come in with the control measures. So as pest management tools, they are used to predict or establish the optimal tactics required to achieve economic control of the pest within constraints of the model. So the model will tell you when the pest will do most of the damage and when are we likely to come in with an intervention to control the pest. So we'll talk about some of these models which are used in insect pests, which are used for diseases and weeds later on in detail. We'll also talk about these economic thresholds. Now, there is a certain population of the pest which may not cause economic problems. But once that population is exceeded, then it will start damaging the crops. That is what we call the economic threshold. The point which the pest population level causes losses greater than the cost of controlling that pest. That is the time to come and intervene. It is the time to come and control that pest. So later on, we will talk about these economic thresholds, how they are actually established. Now, alternatively, modeling, for example, based on weather conditions, can indicate the need to intervene before the pest reaches the economic thresholds, like what happens with the potato blight. With the potato blight, it's something to do with the weather patterns, because potato blight development depends on probably humidity. Now, for cotton, cotton is a good crop because a lot of spraying is done in cotton. So when we are applying pesticides in cotton, it is important that we scout for the insects during the we scout for the pests before we actually spray. When the numbers of natural enemies are high in relation to pest population, probably there is no need to spray. We may have to postpone putting a pesticide, so that we allow the natural enemies to exert pressure on the pests. Or probably we should choose a selective pesticide. Using selective insecticides such as acetamiprid, 50 SL, and the restriction of broad spectrum insecticides, mainly synthetic pyrethroids, to specific periods. So instead of using broad spectrum pesticides, let us try to choose selective ones, which can only target the pest and leave natural enemies. Because sometimes these natural enemies can take care of the pests, and there may not be any need to spray. And we should avoid just spraying unnecessarily. So timing of bollworm insecticide sprays is done after pest scouting to establish the ET values, or the economic threshold values, represented by ET. Pesticide sprays are done after the population of bollworm has reached or exceeded the predetermined threshold values. This can also allow build-up of natural enemies in the field. So when we are spraying, we should take care of these natural enemies. So protecting natural enemies, conserving natural enemies of pests is an important part of IPM and helps to prevent pest resurgence. So the effect of a crop protection product or other intervention on both pests and their natural enemies needs to be considered. So when we use an insecticide, we should make sure that it should not eliminate natural enemies. But of course, in practice, this is not what happens. You know, a lot of natural enemies are destroyed because farmers simply wanted to remove the pest. Timing of application to periods when natural enemies are not active, for example, may help to protect them. If we know the dynamics of our natural enemies, if we know when they are at their peak populations, we should avoid putting pesticides. When they are at their low populations, maybe we come in and put pesticides. We should also select right products, or selecting the right products. What do I mean by this? In developing an IPM program with crop protection products, it is essential to review product characteristics, applications, and costs. Then select the ones that provide the most cost-effective treatment with minimal undesirable effects. Now, some products have broad spectrum activity, while others only target a few types of pests. So we should be in a position to know what insecticide we are going to spray, or what fungicide we are going to spray. I mean, it will be ideal to use very selective pesticides, because selective pesticides are less likely to affect natural enemies and other non-target organisms. But probably they may be very expensive, and also they may not be available. But when we select these pesticides, let us check that they may not affect the natural enemies. Safe and responsible use of products. This is very important. Every crop protection product should be used according to the manufacturer recommendations. Otherwise, if we don't do that, then we have undesirable effects. These products may be designed to provide reliable control under normal field conditions. So this is spraying. We need to prevent the pest resistance to pesticides. But sometimes using pesticides may lead to pest resistance. Now, all farmers are challenged with the fact that pests adapt to active ingredients and eventually become resistant to these pesticides without prevention strategies. But the good thing about IPM is that it offers a range of ways to reduce the risk of resistance developing. So if we are using IPM, we can reduce the development of pesticide resistance. Now, it is important to monitor pest populations and also to use the pesticides if the economic thresholds indicate that it is justifiable to do so. So it is also important to use other alternative methods, just apart from using insecticides. Now let us look at this IPM, plant science industry and the IPM. The global plant science industry has a major role to play in the widespread adoption of IPM. Because IPM needs to be backed by research. There's certain information which it requires. This requires mutual support, partnerships, and collaboration with governments, non-governmental organizations, and research companies, international, national, and local agricultural associations, crop protection, product distributors, dealers, and retailers, and of course, farmers themselves. So a lot of people are really involved with the pest management, especially the integrated pest management. It will involve a lot of organizations. Here I'm going to give you a case study or an example of IPM project which was rated to be successful in Kenya. Now, the problem being addressed by this IPM is the stem borer of maize. On one hand, on the other hand, there is also striga in the system. So in order to solve the problem of stem borers and the striga, it was proposed that intercropping could be used. That is growing maize together with a leguminous plant called the desmodium. So desmodium was grown in between maize crops. What desmodium did was to produce volatile chemicals. These volatile chemicals could drive away stem borers out of the maize field. So the chemicals coming from desmodium are not needed by the stem borers. They would actually drive away the stem borers from the maize. And at the edges, they grew napier grass outside the maize, at the edges of the field. Now, napier grass would then attract, it would also produce volatile chemicals to attract stem borers. So the stem borers ended up in the napier grass, and they would lay their eggs there. So they were diverted from the maize, and they will no longer damage the maize. At the same time, desmodium produced chemicals which interfered with the striga. So striga could also be controlled. In addition, desmodium also fixed nitrogen and supplied nutrients to the maize. So this was quite a good system. It is known as the pull and the push system. The pull in the sense that napier grass is pulling the stem borers, and the desmodium is pushing out the stem borers out of the field, which are being pulled by the napier grass. So this system could solve the stem borer problem in maize, as well as the striga problem in maize. Well, this is the push and pull for stem borer and striga control and improvement of soil fertility. Well, these are the chemicals which are involved in the pull and the push system. I've already tried to explain these issues. So the push and the pull strategy, as it was called or termed, it was developed over the past 6 years as an integrated approach that simultaneously addresses both the major problems. The push and pull involves trapping stem borers on highly attractive trap plants, the pull, and driving them away from the maize crop using the repellent intercrop, the push. Plants which repair stem borers as well as inhibit striker have also been identified. Now, this is the work of ISIPE, which is based in Kenya. Now, they've used trap or repellent plants. They used Napier grass or Penicetum peperium, Sudani grass, Sodum vulgare, Sudanins, then molasses grass, Melenis muniflora. They've also used the silver leaf, desmodium, and the green leaf desmodium. Now, Napier grass and Sudan grass have shown potential for use as trap plants. Whereas molasses grass and the silver leaf desmodium repel ovipositing stem borers. Molasses grass, when intercropped with maize, not only reduce infestation of the maize by stem borers, but also increase stem borer parasitism by a natural enemy, Cortesia sesamia. Desmodium, when intercropped with the maize, can inhibit striga. So this is the push and pull strategy. It's a planting strategy which can solve the pest problem. This is an example of IPM, Integrated Pest Management. Now, in conclusion, we can say that there is no single pest control tactic which is relied on in IPM systems. So you need several control tactics to integrate. Pesticides are used only when needed in relation to ETs, economic thresholds. And it is important to use them judiciously so that we don't put too much of these pesticides. Well, there are opportunities to design and exploit IPM strategies to control pests in Zimbabwe. So there are opportunities for developing these strategies in this country. Well, there's a video about the Kenyan example of IPM, which I have embedded in your notes, which you can play. I don't think I will play the whole video.
To work on her push-pull field this April. She has been using this method to grow maize for 12 years now, and it has dramatically changed her life and that of her family. A mature push-pull field needs regular attention from sowing to harvest, but nothing like the initial effort required to establish one to replace a field ravaged by the striga weed, infested by the stem borer, and lacking fertile soil. At 52, Agnes can look back on a real success story after plucking up the courage in 2002 to try out the then still quite
Okay. If you want to play that video in full, you can follow it up. It's about integrated pest management. So I'm going to stop here. Okay, so this was about integrated pest management, quite a long thing. But for you, you need to remember that there are three things. Prevention. If you can remember something on prevention, then monitoring. We should establish pest populations so that we decide when to come in and put in chemicals. Then intervention. This is the actual control methods which we can harness to reduce the populations of these pests. And that's all about integrated pest management. Three things: prevention, monitoring, and intervention. So later on, I will expand on some of the issues which we have talked about, especially monitoring. I will talk about how we can monitor pests, insect pests, weeds, diseases, and how we can use that information to predict crop yield losses, and how we can use that information to establish economic thresholds. So that is what I will talk about in the next lecture later on. So let me stop recording.